There is a special case of recursion in which a function is recursively called as the very last thing in that function. This is called tail recursion. What makes tail recursion special compared to normal recursion is that it affords a very big optimization. Normally, when you call a function, every function call requires its own stack frame. It requires more memory. However, in a function call, when you make your very last call, when you do your very last thing, you know that you're not coming back, so you're not going to be using the local variables again. So you can just discard the frame for that call. What this means with tail recursion is that, say the function is recursively called 1,000 times. Without this optimization, you would end up having 1,000 stack frames, but with this optimization, you only need one. Every time you make another tail recursive call, you just overwrite the existing frame. You don't make a new one. On a modern system, this not only has the benefit of using less memory, it also actually can be a considerable speed up in execution, because modern CPUs rely heavily upon caches, and so if you don't exceed that cache, your code is likely to go much faster. Now, in most dialects of Lisp, the compiler itself will identify these cases of tail recursion and automatically make this optimization. In Clojure, however, because the JVM itself doesn't have any optimization for tail recursion, you have to explicitly denote these tail recursive calls yourself. So to do this, we have the special form recur. You use recur by simply providing the arguments for the recursive call that you're making. It's just like making a recursive call, except actually the compiler will check and make sure that recur is used only in the tail position of the function. It has to be in the place where it's going to be the very last thing potentially done in the function. So here, for example, we have a function which takes in a parameter. It prints the value of that parameter, and then if that value is less than 1,000, it will call the function again, except with that value, that parameter, plus 4. So if we call mouse with the argument 7, what you will see is first 7, then 11, 15, 19, 23, 27, and so forth, up until the time in which the call where parameter is greater than 1,000, then it will stop. And because this function uses recur to make its recursive calls, a call to the function will only ever take up one stack frame. The special form loop is actually just like let, but with one small difference. Like let, loop is a block of code in which you can bind some values to some names at the start, but the difference is that if you call recur in the loop, then it takes you back to the top and rebinds values to those names. So here, for instance, we are binding to the name A the value 7, and then we execute the body of the loop. So first we print A, and we test, is A less than 1,000? Yes, it is. 7 is less than 1,000. So we call recur with one argument, which is A plus 4. So we call recur with the argument 11. And the recur here means that we execute the loop again, except this time instead of binding 7 to A, we bind 11, because that was the argument to recur. So this code is actually functionally equivalent to what we saw in the previous slide. It's just that we don't have to create any function and then call it. And again here, recur has to be used in tail position, so it can do the tail recursion optimization. Two more special forms I'll briefly mention. There's throw and there's try. And as you probably imagine, they are how you both throw Java exceptions and how you catch them in your Clojure code. I'll just refer you to the Clojure documentation where you can see exactly how they're used. Now that we've covered the special forms, we should clarify exactly what happens in the evaluation stage. Evaluation you should think of as happening actually in two stages. First, there's the compile stage and the execution stage. In the compile stage, the evaluator looks at the reader data and it analyzes all of the special forms and it resolves the symbols, but it's not until the execution phase that the special forms actually do their effects and the functions are called. One reason for this separation is really just a matter of efficiency. The compile phase really does compile. It compiles into Java bytecode, and then it's this bytecode which is executed. You're also probably wondering what the distinction is between analyzing special forms and special forms actually taking effect. Well, say when you analyze the special form if, what you're doing is you're putting into the compile code a branch, but it's not until execution time does the branch actually get taken. Does it actually test the condition and take one of the two branches? Similarly, when the compiler analyzes the special forms let and fn and looks at the names and the parameters, that's where it does the lexical scoping and decides what names belong to what scopes. but it's not until execution time that these names get actual values. The fact that symbols are resolved at compile time has an important and probably unexpected consequence. In most modern languages, the order in which you define your functions generally doesn't matter, and this is the case even in dynamic languages like Python or JavaScript. However, what's going to happen here in Clojure in this top line is, assuming that the symbol frog is not in the current namespace, this top line will throw an error. The compiler simply expects to resolve all symbols either to some var in a namespace or to a local name, such as a parameter in a function or a name in a let. So what we have to do to fix this is to either reorder our definitions, or we just simply need to add a definition for frog before we actually define the real function. If you simply write def frog, that's going to create a symbol var mapping of frog to some var in the current namespace. That var simply just isn't going to have any value. In fact, it's going to be unbound. It's not even going to have the value nil. But that's okay, because all we need at compile time is for the compiler to find some var. Because vars are mutable, we can just change it later. In fact, this should drive home the point that Clojure really is a dynamic language. At compile time, the function that's being bound to duck here calls some var, and the thing held in that var is free to change at any time. In my description of the compilation phase, I actually left out one important step, and that's the processing of macros. So you're wondering, what is a macro? Well, in Lisp, a macro is really just a function that takes data from the reader and modifies it. Macros transform the reader data before the reader data gets compiled into bytecode. The point of this is basically that we can write macro functions that effectively serve as syntactical conveniences. In Lisp, if you find that you keep writing the same boilerplate code over and over, you can often solve that problem by creating a macro. So let's start with a contrived example and say that the symbol monkey resolves in the current namespace to a var containing a macro function. What the compiler will do then, before analyzing the special forms and generating bytecode, is it will call this macro function, and the arguments will be, first, a list containing the symbol raccoon 1 and 2, and the vector containing 4, 5, and 6. Those are its two arguments, the list and then the vector, because that is the reader data. The way we usually put this is that the macro gets its arguments unevaluated. It just gets the reader data, not the values returned by compiling and executing that data, just the reader data. So the macro executes with these arguments, and eventually it returns a value, and it's this value which gets put back in the reader data in place of where the macro call was. So if this is what the macro call transforms into, then what happened is it returned a list, starting with the symbol print, and then another list, the list that was passed in, and then a string saying yo, and then the other argument that was passed in. Be clear that it's entirely up to the macro what gets returned. This is a silly example, but typically a macro will take the unevaluated input and it will put some sort of stuff around it, maybe rearrange it in some way. Again, the idea is that macros serve as syntactical convenience. They're a way of doing syntactical compression. It's also important to understand that macros are processed first inside out. That is, so say here that monkey and raccoon were both macros. Well, because monkey is the outer one, that's the one that's going to get processed first. But macros are also processed recursively, meaning that if there are any macro calls in what gets returned by a macro, then they get processed too. So here in what gets returned from the macro monkey, raccoon might also be a macro, and that will get processed in turn. So here's an example of a macro which is actually useful. Defn is a macro in the namespace clojure.core, and when we call it like this, what we get back, what it expands into, as we say, is a def to a function. In fact, this is actually the preferred way of defining a function.